Okay, so we can start today's session with a look at the assignment 4D. I had sent an email suggesting that questions 1 through to 13 can be done for assignment 4D. If you have completed the assignment, then if there are any questions that you would like to discuss at the beginning, we can start with that. Otherwise, we should move straight into factors affecting critical angle, where we left off yesterday. Okay. I had sent an email right after the class got over when Amresh sir's class was going on. I don't know. We had to do something 13. Okay, Ak seems to know. He has checked his email. Harshita has checked it. Yeah, okay, it's fine. So if you haven't completed it, do make sure that you complete it by tomorrow's class. So then if there is nothing left to do, we can move on. Who's calling? Who's asking? Who's speaking?
Yeah, so I have a question.
Hardik, yeah.
Yeah, so question number 7.
Question number 7, okay.
Yeah, so I didn't get the part that more than 45 degrees, less than 45 degrees.
So the question goes, the critical angle for glass air is 45 degrees for the light of yellow color. Okay. State whether it will be less than, equal to, or more than 45 degrees for red light and blue light. See, this basically follows from the fact that when light passes through a prism, we will come to see this a little later when we study dispersion. What we see is that I see it's asking the critical angle for yellow light. Okay. More than 45, less than 45. Okay. Uh, did anybody else attempt that question while I look it up? Could somebody else answer?
It's there in passage of reflection, depending on the color.
Yeah, so critical angle depends on the color.
Yeah, like I got it that it depends on the color, but then there is no
Yeah, so
definite explanation.
okay, so very good. So this kind of picks it up directly from what we were discussing just yesterday, the last point that we had discussed, factors affecting the critical angle on page 94. So it says over there that the critical angle for a pair of media is least for the violet light and most for the red light. Okay, so if yellow, which presumably lies somewhere in between these two, is going to be 45 degrees, right? Then the red light, and for the violet light, by blue they mean something in the violet region, is going to be, so for red light is going to be more than 45 degrees, and for anything in the violet region it's going to be less than 45 degrees. But you'd have to think through the concept to understand. So Aks is saying it's higher with greater wavelength, so red is more and blue is less than yellow. Does that satisfy you, Hardik?
Yeah, somewhat. I got the basic idea
Okay.
now. So
I mean, I'm not expecting questions like this to come, but it's good to know that that is how you test whether you have understood the relationship between the wavelength and the critical angle. Okay, it's
yeah.
fairly obvious that it depends on the wavelength, but in what way will it affect, and in which wavelength, towards which wavelength, towards the red or towards the blue, will it increase or decrease? That you got to work it out for yourself. Okay, so I'd say that's the chance of such a question being asked is diminishingly small, but cannot be completely overruled. Ishrat's Wi-Fi died. Oh, what a pity. let's observe 2 second silence for Ishrat's Wi-Fi. Okay, so let's start. So to move on from factors affecting critical angle, let's come to the conditions for TIR to take place. So that's where we left off yesterday. Okay, let me go back to screen sharing. So conditions for TIR to occur is fairly straightforward. There are only two conditions that are given in the textbook. One is that the light must travel from denser to rarer medium. Okay, so that's an obvious condition. When it goes from rarer to a denser medium, there is no question of any TIR taking place. Now, as a statement, okay, it's pretty straightforward. But to understand why it will not occur, actually, then you have to use Snell's law, and there is a lecture by Professor Walter Lewin that I would like you people to see if you want to know more about this. This is in his lecture series on electromagnetic radiation, electromagnetism. Okay, and in that the lecture 26. Okay, so this is a 1 hour lecture on refraction, and there are a lot of concepts that we are studying that he picks it up over there. And in that somewhere around the 10 to 15 minute mark, he talks about critical angle, the why of the critical angle. Anybody who's interested can look up that lecture, and then you can write back to me. Anybody who is having any further questions or anything that they want to discuss, a few of them have been writing into me by email. And I have also been it's also been interesting for me to reply to their queries. There's a lot of learning that happens, there's a lot of thinking through that happens in that process as well. So anybody who's interested in picking something up and examining it a little more closely, do please write to me. I'd again like to remind you that the Tarashova and Toroshova discussions on refraction of light that I had sent by PDF by email is also an excellent book to look into. Very simply written, there is no complications in it, and the chapters have also been divided into something that kind of is very favorable to us. So one of the chapters, the chapter that we are discussing right now, is refraction through prism. I think it's the third chapter or fourth chapter, I'm not sure which, in which there is a detailed discussion of this the minimum angle deviation and so on. So please do look into that also. Spend some time studying these things, and you will not be sorry about that. Now, the second point, the essential conditions for total internal reflection to be taking place is then obviously incident angle should be greater than critical angle for that pair of media. So this is also fairly obvious. So if if the angle of incidence on the boundary between the two media, the denser media to rarer media, if it is going to be lesser than the critical angle, or even at the critical angle, there's not going to be any total internal reflection taking place. So the critical angle has to be exceeded in order for total internal reflection to take place. So these 2 points are fairly straightforward and logical, and it should not pose any problems for anybody to remember that. So now we move on to the next part of it, which is total internal reflection as it takes place in a prism. So TIR in prism. So before we move on to that, anything that you would like me to talk about? Any questions? Okay. So moving on. All right. So as far as TIR in a prism is concerned, um, obviously we are not talking about the refraction taking place at the first surface of the prism. So we'll take the simplest scenario. We take a right angle prism. Okay, so this is of course the face of the prism. The prism itself will kind of look like this, right? Okay, so that's the prism, and this is the right angle over here. Okay, so we are talking about the ray of light striking the prism like so. Let me change the color there. Okay, so now what's going to happen? So yeah, let me mention that the angle over here is a right angle, 90 degrees. Okay, and since it's a right angle, what is it, isosceles, right? So this will be 90 degrees, and these two will be 45 and 45, right? Yep. So what's going to happen? No refraction. Yeah. So since this ray of light is coming along the normal, you see, any doubt, always draw the normal. It's coming along the normal, so there is going to be no refraction. The ray of light is going to pass through undeviated. We say pass through undeviated and strike the face of the prism on the hypotenuse side, on the longer side. Okay, so now at that face we have to decide what is going to happen. Well, again, whenever in doubt, draw the normal. So I want to know what is the angle of incidence over there. So I need to figure out what is this. Okay, so now you have to apply a little bit of your knowledge of geometry to this. Work out the angles of this prism. So if this is 90 degrees, then obviously this is also 90 degrees. If this is 45, then this is also 45. If this is 45, then this being the right angle, you see this is the normal. This is also 45. Okay, is this clear? Normal isn't visible. Yeah, somebody made off with my green marker. So I'm stuck with a dud green marker. I'll get another one by tomorrow. Okay, so maybe this angle also I'll write it a little larger. So therefore this angle is also 45 degrees. So you see, now since this is glass and this medium is presumably air, the angle of incidence being 45 degrees, it exceeds the critical angle. You see, the critical angle for glass air interface is approximately 42 degrees, right? So since the angle of incidence is 45 degrees, then there is going to be TIR taking place. Why? Because you see the two conditions are met. The light is traveling from denser medium to rarer medium. So this is the denser medium, this is the rarer medium. It's going from the denser medium towards the rarer medium. Maybe must travel, maybe this from should be actually be towards, because it's actually never going to get there. Travel denser medium. Oh, shucks. Sorry, that was the wrong word to change. From denser to rarer medium. I think that's correct then. So that's not a problem. And then the second condition is the incident angle, which is this angle, has to be greater than the critical angle. Critical angle is 42 degrees, which you expected to remember. So therefore, there is going to be a reflection, a total internal reflection taking place. Okay, so now again, see, these are all set pieces in the sense that if you see a certain angle, a certain type of prism, then you should immediately know what is going to happen next. But in order to know, see, from the exam point of view, you don't want to waste time working out the angles unless they have given you something unexpected. So from an exam point of view, it is good if you practice a little bit and you know exactly what is going to happen. So when that happens, you know that this angle is also 45 degrees because it's going to obey your laws of reflection. Now, if this angle is 45 degrees, this angle is also 45 degrees, this angle is also 45 degrees. So therefore, the angle of incidence over here is going to be 90 degrees. So it's along the normal over here. So this ray of light is also going to pass through undeviated. So this is a typical kind of a board question that you can expect. They will give you a diagram, they will show you the incident ray, they will tell you what is the medium, and they'll ask you to complete the diagram until the ray emerges outside the prism. Okay, so this is something that you will do well to practice. It's there on page 95 onwards, and there are 2 or 3 such diagrams that you should be expected to complete. Now, um, another interesting thing to notice over here is that you can also work out the angle of deviation for this. How will you do that? Well, the path of the ray of light is like this. Okay, it would have passed on in this direction if not for the prism, and it has now turned through this angle, so it's now coming in this direction. So what is the angle of deviation from here to here? Delta, that is equal to 90 degrees. So what you have done in effect is you have turned the path of the incident ray by an angle of 90 degrees. Okay, and this is a very interesting thing. I'll talk a little bit later about the applications of TIR in prisms. It has some very important applications as far as optical instruments, telescopes, camera, binoculars are concerned. And I'll discuss that a little bit later. So now moving on to, is it possible to now create an angle of deviation of 180 degrees? Yeah, it turns out that it is possible to do that. The diagram is given on page 96. You can look it up. But all you need to do is you need to change the orientation at which the light ray hits the prism. Okay. Saumitri says may be able to do practicals with laser. This one's used for periscope, that is 90-degree deviation. Yeah, that's right. You can use an arrangement of 2 prisms like this in order to uh, make a periscope. The question is, why not use a mirror? When we do a junior school or a middle school science project to do a periscope, we usually use mirrors to do it. Okay, and it works pretty well. Question is, why do we use prisms? What is the advantage? Okay, so we'll come to that in a little while. So now we are back to this prism business. We have a right angle prism over here. In this case, the 90 degrees there, and these two are 45 degrees. Okay, and now a ray of light is incident on the hypotenuse at an angle of 90 degrees. All right, so again, as usual, since it's approaching along the normal, by definition there is not going to be any deviation taking place. This light ray is going to go ahead and strike the nearest inclined face over there. Now, since we have already seen over here what happens when a ray of light passes unmolested and it hits undeviated, sorry, and it hits the hypotenuse on the other side, we'll immediately know that this is 90 degrees, this is 45 degrees. And since that is 45 degrees, the angle of incidence is also 45 degrees. So there's going to be a total internal reflection taking place over there. Okay. Now this is going to hit over here. Again, if you look at the normal over here, if this is 90 degrees, this is 45 degrees. If this is 45 degrees, this is also 45 degrees. If this is 45 degrees, then there is going to be TIR again taking place. Okay, so this is 45, TIR takes place. Again over here, the angle of incidence coming from glass into air is 90 degrees. And when it strikes at 90 degrees, TIR won't take place, mind you. At an angle of incidence, uh, which is 90 degrees, even though it is light traveling from denser medium to rarer medium, and the incident angle happens to be greater than the critical angle, no, it's not, right? The incident angle is actually 0 degrees. So then the condition is not met. So therefore, it's going to come out undeviated. And in this case, if you see, the direction of the light was in this direction, right? And it comes out in this direction. So your delta in this case is going to be 180 degrees. That means it has turned the light completely around.
So this whole thing is delta.
Yeah, yeah, that whole turn is delta. Isha was just asking if Isha is attending the class over here live. Yes, that's right. So why use a prism? So several have given the answer. The reason why you use prisms for real life applications is simply because there is no loss of intensity of light at all in this case, because it's TIR, it's total internal reflection. Whereas in the case of mirrors, you are likely to have some loss intensity because of multiple reflections. Otherwise, you will have to go for the mirrors which have the the mirroring surface on the front rather than in the back. And if you do that, then that is an exposed surface. Over a period of time, you're going to have some of the silvering wearing off. So if you want long lasting optical instruments, and you also want zero loss of light intensity, then that is the reason why we go for prisms. Yes, that's right, Soumitra. It lasts longer. The plane mirror silvering will fade off over time. So for those two reasons, and it's easy to work that out. Uh, now there is just one more case, but I'll allow you people to work that out, which is in the same arrangement of the prism. If you have a light ray, maybe, okay, I'll just show it very quickly. Same arrangement. If you have a light ray which is coming parallel to the base, right? This is parallel to the base. Then what happens? Again, you can work out all the, in this case, you just have to draw the diagram a little carefully, draw it a little low over here. Okay, the ray of light will be incident like that. So this is going to refract, and over here you will find that the angle of incidence is higher than 42 degrees, will be higher than 42 degrees. So it will reflect over here, and then at this face again it's going to emerge out here. So the emergent ray is going to be again parallel to the base. Okay, so this I will let you people figure it out. I won't explain it entirely. This is figure 4.49 on page 96. Okay, so you people can go ahead and do that. um, Now a similar thing can also be done for your 30, 90, 60 degree prism as well. Okay, so that's also something that is asked once in a while in the board papers, which is that these prisms where you have a 90 degree here, this is a 30 degrees and this is a 60 degrees, and you could be asked a variety of questions. You could have an incident ray which is incident to the base like this. This is one scenario. You could have an incident ray which is perpendicular to this surface over here. This is another scenario, and of course you can also have a ray which is incident on the hypotenuse. This is the third scenario. So work out all these different possibilities. They will not give you any possibility in which you have to apply Snell's law in order to figure out what is the angle of refraction. So by just simply using angle properties, you should be able to work out the entire path of the ray until it emerges from the prism. Um, the 60-degree prism, no, it's there as part of the syllabus. They just generally don't ask it very often in the board papers, is my feeling, gut feeling. I don't remember very well, but I haven't seen it for a while now. So even if they do ask, it's not really a problem. Most of the question is going to be, light ray entering perpendicular to this surface, or this surface. So if that is the case, then you should be easily able to work out the angle properties. All right. So now we should move on. Let's look at what's next. The uses of total internal reflection of prism in place of a plane mirror. Well, so on page 98, you have a table that is given, which gives the distinction between total internal reflection uh, from a prism as the advantages of TIR over reflection from a plane mirror, like it was observed by other people. Um, the reason why we use prisms is that in TIR there is no loss of intensity. Um, they are giving 3 points over there. I don't. Yeah, you can. There are 4 points given. Beg your pardon. So you can have a look at those 4 points just in case they want you to give two distinctions between TIR and reflection from a plane mirror. Unlikely question, so I will not go into it. But for those who are interested, please have a look. So I'm more interested now in looking at some consequences of total internal reflection. Okay, so there are a few things that you can share. Okay, so now we come to this part where we are looking at some interesting TIR related phenomena. So one is mirages. Okay, so many of you would have seen mirages. I doubt there will be anybody who hasn't, but basically the phenomenon occurs when you're either walking over a flat ground on a hot day, on a hot afternoon, or more likely when you're driving in a car and there is a highway, straight wide highway in front of you, and you can see for a few kilometers ahead. Now what happens is you seem to see that there is water somewhere at the distance, and while obviously there is not going to be any water body on top of the road as you're driving. So I have always found it difficult to imagine that somebody would actually mistake it for water that is there on the road. But it can be pretty convincing, and this has got something to do with TIR, total internal reflection. For you see, what happens is, so I have a picture over here. Yeah, this one. Can you all see the image clearly?
Yeah.
Okay.
Yeah.
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 So I guess yeah. So I guess I actually found this picture a little difficult to believe that it actually looks like this. It really looked like water on the ground. But I guess what they have done is they have taken. Hey, can you get rid of all that graphics on it? Yeah, thank you. Who's that, by the way?
Oh God. Why?
Stop it. Get rid of it. I'm not starting until you stop doing that. Okay. How I guess they took this picture is they took a long shot, and there was the mirage that was visible at the distance, and then they cropped it and enlarged the picture. That's my guess. But anyway, let's get back to this. So how is this happening? Well, what's happening on a hot day is that the tar road, which is black, obviously gets heated up more than the surrounding. Okay, so there's vegetation there. That's not likely to get heated up. Now, when the ground gets heated up, it heats up the air right above it. Okay, and when the air gets heated up, its density goes down, right? So the air which is above the low density air is going to be still having higher density. All right. So to come back to the board, um, what we are looking at is let's say that this is the surface of the road. Okay, let's just look at it like this, cross section. So this is the surface of the road. Now, because of the incoming solar radiation, so the air which is just above it also gets hot, right? So let's say there's a slab of air like that which gets hot. Now this is at low density compared to the air molecules which are above it, which are presumably at a higher density. Okay, this is going to take a little bit of time. All right. So low density, and this is higher density. So now what happens is there is incoming solar radiation from, let's say, from here. And basically this is light that is coming from the sky. Okay, so it's mostly blue light. That is because of the scatter that takes place, but I'll come to that later. And now when it goes from this density into this density, right, what is happening over here? Light is going from a higher density to a lower density, right? And when it goes from a higher density to lower density, it is possible that TIR can take place, correct? TIR is possible. Now, what is the second condition that has to be satisfied? The angle of incidence over here has to exceed the critical angle. Well, obviously, it must be exceeding the critical angle. We do not know what is the critical angle for this two pair of medium. I suppose it can be worked out, but we do not know it. But since we do see a reflection of the sky, 3 minutes left for class. Okay, yeah. So in case the class gets over, we will rejoin after this. Yeah, we have about 10 minutes of time left, so we'll do that. And therefore, there is going to be a reflection taking place over here. Okay, so people over here who will be looking at this, right, are going to see light from the sky getting reflected and coming over there. All right, so far so good. So then you should be just seeing blue color. I I can't see properly. It's all blurry. Yeah, I tried to draw it as large as possible. And my voice is also breaking. Okay. Yeah, maybe the bandwidth is reducing. I'm not sure. Okay. Anyways, in any case, we are kind of running out of time right now. So just join me quickly after this. Okay. I'll stop it and I'll start the meeting again.